Okay, so today I want to continue on in chapter 2. We're talking about alkanes and cycloalkanes in this chapter principally. I want to leave cycloalkanes for Wednesday and all of the conformational stuff. If we have a little bit of time at the end of the class to talk about conformations of ethane, great. If not, and that has to wait until the next class, that's also fine. Because I was thinking when I was almost over here, it probably wouldn't have been a terrible thing if I had my molecular models with me. And I certainly will want to bring them for the next class since we have a document camera. So, but in terms of properties, reactions of alkanes, what we're going to find is there's not very much to say. Alkanes are very inert. They don't undergo very many reactions at all. We're only going to talk about 2, and that's about it. And I almost want to say 1.5 reactions, since I almost don't even know if you want to count combustion as a reaction. In any case, you covered that in Gen Chem. But there's really only one new reaction of alkanes that I want to talk about. And then another thing that's kind of like resonance that I think is often easily misunderstood even after some background in Gen Chem is intermolecular forces. So I would like to do a fairly concise review on that if I possibly can. The reason it's in this chapter is because there are some intermolecular forces like van der Waals forces that apply especially to alkanes, and some like hydrogen bonding that especially don't apply to alkanes. So I just wanted to make those distinctions for us. And like I said, if I have a chance to talk a little bit about ethane, great. If not, I won't cry over it. And I'm sure you guys won't either. Good, so I thought I'd start with a couple more examples of naming alkanes. I understand it's not the most interesting topic in the world, but at the same time, it's a bit complicated the first time through. There's a lot of moving parts. Hopefully you've practiced that some over the weekend. But I wanted to do one more example like we did in class the other day. And I also thought I'd do an example of going in the opposite direction, from the name to the structure. I don't know if you guys will largely agree with me. I always find it more difficult to go from the structure to the name than to go from the name to the structure. I find going in the opposite direction to be much easier. And you don't have to agree with me. We'll see what you think. So let's take a look at this compound. Our first goal needs to be to find the longest possible carbon chain. And we want to search down all possibilities to make sure that we find the longest continuous chain of carbon. So the one that includes the most carbon atoms without, so to speak, taking your pencil off the paper. So 1, 2, 3, 4, 5, 6, 7. We got 1, 2, 3, 4, 5, 6, 7. Can we get a longer one? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. No, I think 7 is going to be the longest one. So the next challenge is numbering the carbons. And you want to do so in such a way that we start nearer the nearest to the first branch point, because that's going to ensure that that we get the lowest possible sum when we add up all the numbers at the end. And if that is difficult and concerning to you, again, you can do like we did last time. You can just number both ways and then pick the best name from that. I think we will get the best possible name if we start numbering over here. Because that way, the first branch is going to be on carbon 3. By branch, I mean the first thing that's attached that isn't an H. The first thing that's attached that isn't an H. That's what I mean by a branch. That's the definition. And I think you'll see if we started here, we go 1, 2, 3, 4. And so we would start at 4 instead of at 3. So I think that's the best place to start. Is it okay for me to do that, or would you rather I do the thing where I number both ways? Or do everyone kind of sees? Okay. And like I said, that's always an option. It's never wrong. You just might be able to save yourself some time. But if you'd rather do it that way, feel free. It's never wrong to do it the other way. So it looks to me like we have an ethyl group in carbon 3 of our heptane because 7 carbons. And it looks like we have an isopropyl group on carbon 4. And that's not the only correct way to draw an isopropyl group, but I do expect you to know those alkyl groups: methyl, ethyl, both propyls, and all 4 butyl groups. You need to know all 4 butyl groups, but I think the 2 types of butyl groups you'll see the most often are N-butyl and tert-butyl. Those seem to me to be more common than either sec-butyl or isobutyl. But in any case, we've got an ethyl group in carbon 3 and an isopropyl group on carbon 4. So all we need to do is say that there's 3 ethyl, 4 isopropyl, and then just call it heptane, because it's going to be based on a 7-carbon chain. So I think that's the best name. We want to go alphabetically: 3 ethyl, 4 isopropyl, heptane. So I think that's the best name. Had we gone the other direction, I think we'd find 4 ethyl, 5 isopropyl, and that adds up to 9, where 3 and 4 add up to 7. So I'm pretty sure that's the best name. It's all one word. OWL can sometimes be picky about hyphens and the like, so please notice the placement of hyphens, commas, other punctuation like that. But I think that's the best name. Make sense? Questions on that one? Well, let's move on to 4-bromo 2,2-dimethylhexane. Well, it's named as a hexane, so we have to have 6 carbons: 1, 2, 3, 4, 5, 6. And if you'd rather do it this way, actually, I'm going to think ahead a little bit. One, 2, 3, 4. I think that should be enough. 1, 2, 3, 4, 5, 6. Same thing. So we want to, as we count the carbons, you can start on either side. That's part of the reason why going from the name to the structure is something, at least I find it easier to go the opposite way. But actually, I didn't exactly make that very easy for myself. Let me think ahead a little bit. 2, 3, 4, 5, 6. There we go. So now we need to put 2 methyls in carbon 2. 1, 2. And we need to put a bromine in carbon 4. And since as I said, at least through the first exam, let's put in all of our non-bonding lone pairs. After that, we can begin to relax a little bit. I just want everyone to get used to following the octet rule and looking to make sure that all atoms have the correct valence. So I think that's the best answer. In a later chapter, we're actually going to learn there's 2 different 4-bromo 2,2-dimethylhexanes, because this carbon over here, we'll learn in a later chapter, has a property, it's called a chiral carbonyl, which means it exists in both left and right-handed versions. We're not going to worry about that for now. And I think even most of the times we won't worry too much about that. But just so you know, that's coming down the pike. If you wanted to use the line angle drawings, then we would want to put, well, here's 1, 2, 3, 4, 5, 6. You would want to put 2 methyl groups in carbon 2 and a bromine in carbon 4. And then, of course, be sure to fill in your other valences to make sure that all carbons obey the octet rule. So that's another correct way of drawing that compound. You could also have drawn the molecule turned in the opposite direction. Totally fine. So it's important to be able to tell whether 2 drawings are of the same molecule or of isomers. Yes. Is methyl like a V? I'm going to say no. The methyl groups are, I think I know what you mean, though I'm going to double check. The methyl groups are are any 2 of those 3 things. So the way you know that is you see like that sharp point or corner, that's a carbon atom. And off of all of them, we see only one line, only one of the bonds is shown. So that means the other 3 bonds have to be the hydrogens. So of those 3 methyl groups, 2 are the methyl groups in the name. The other one is part of the hexane chain. Is that kind of what you meant? Just wanted to make sure. Good. Yes. Oh, did I mess that? I was worried that I'd messed it up. I actually got it right. The reason the bromo comes first is because B comes before M, and you go alphabetically. I meant to mention that over here because you've got E coming before both I and P. I think it's technically the P that we count in isopropyl, not the I. But I very cleverly carefully picked that so that it would go before both of them. So I removed the option. But yes, when you're in doubt, you want to go in alphabetical order for the substituent groups. Other questions? So I don't want to bore you anymore, since, like I said, I'm well aware it's not the most fascinating topic in the world, but I figured a couple more examples would probably do no harm. Good. Well, let's see then. Get to where we were in our notes. So much for naming alkanes. And like I said, you'll get plenty of practice with that on the Chapter 2 OWL assignment. Also with naming cycloalkanes, which, by the way, are not, naming cycloalkanes is not significantly different from naming alkanes. We'll do a couple examples next time. But I would say if you can name an acyclic alkane, you can name a cycloalkane also. So we'll talk more about that next time when we get into also conformations and other properties of cycloalkanes. But that's really what today's lecture is about, is more on properties and reactions of alkanes. In terms of reactions of alkanes, as I said, there's really only two, and one of them you knew about from Gen Chem, which is combustion. And I think, I don't know if combustion is a word we use every day, but I think we all understand it means burning something. And that's all that combustion is. Combustion is the rapid combination with oxygen, which our air is about 20% oxygen, and most of the rest is nitrogen. But when oxygen combines rapidly with something, we call that combustion or burning. And I think you're familiar with that process. But in general, I'm taking it for granted that you covered balancing equations in Gen Chem. Generally, combustion equations are pretty easy to balance. So if we were doing the combustion of, let's say, butane, or one of the isomers of C4H10, could be either butane or isobutane, in fact, combustion is going to refer to the combination with oxygen. And of course, molecular oxygen is O2, right? That's one of your Hankelbrief elements. Did you talk about the Hankelbrief? Those elements that exist as diatomic molecules in their most stable state. Hankelbrief or Brinkelhoff, what is it? Hydrogen, oxygen, nitrogen, chlorine, iodine, fluorine, bromine. Those all exist as diatomic molecules in their most stable state. And the products are always the same. They're going to be carbon dioxide and water. And so these are generally pretty straightforward to balance by inspection. You don't have any of that evil stuff like redox reactions where you have to worry about multiple oxidation states and drive yourself insane. Nothing like that going on here. So you just balance it by inspection. I see we have 4 carbons on this side, so that means we need 4 CO2s. Over on the other side, I noticed that we have 10 hydrogens, so we'll need 5 H2Os, because all of the hydrogen will go into water. And then we balance, it's general best practice to balance any uncombined elements last, because they're the easiest ones. So 4 times 2 is 8, 8 and 5 more oxygens in the 5 waters makes 13. So to get 13 oxygens, we need 13 halves. And a lot of textbooks are really not big fans of fractional coefficients. I see no problem. I have no problem with an occasional simple fraction like that. If you wanted to, you could also just multiply everything by 2, and you'd get 2 C4H10s, 13 O2s, 8 CO2s, and 10 water. Perfectly fine. I think both are equally correct. Or just to do another example of balancing these things, if we did any of the heptane isomers, and we wanted to talk about their combination with oxygen to give CO2 and water, pretty easy to do so. 7 carbons in C7H16, so we need 7 CO2s. We've got 16 H's, that means we need 8 H2Os, 8 times 2 is 16. And then we add up all of our oxygens, 7 times 2 is 14, plus 8 more makes 22. So I conclude we need 11 O2. Wait, did I do that right? Because I have 15 in my notes. Let's try that again. 7 times 2 is 14, plus 8 is 22. Am I losing my mind? Well, okay, I'm losing my mind. Did I screw that up? Because I think my notes are wrong. 11 times 2 is 22. We're good, right? wish there were a lost writing utensil up here so that I could fix my notes. Well, be that as it may, these are generally pretty straightforward to balance just by inspection. I'll have to make that change later. Good. So combustion is one of the, I should even write combustion over here. Combustion of alkanes. What about halogenation of alkanes? We can even put here combustion of alkanes. What if we wrote reaction? Can I go RXN for reaction with O2? And then for halogenation, let's put reaction with Cl2 or Br2. And I think you'll find in general halogenations are going to be reactions with chlorine or bromine. F2, elemental fluorine, is much too reactive to get any kind of controlled reaction with an alkane. It'll just tear the molecule apart and give you CF4 and HCF3 and things like that. It's too reactive. Iodine is the opposite problem. Iodine is not reactive enough. If you add iodine to an alkane, they'll just look at each other, no reaction. But chlorine and bromine seem to be just right. And in general, in the halogenation of an alkane, what you'll find is there's going to be some hydrogen somewhere on our alkane molecule, of which there are several. We've got lots of choices. And just get rid of all this mess. And we're going to combine it with, let's say, X2, where X is chlorine or bromine. So either Cl2 or Br2. And in the end, generally this requires either heat or light. The reaction can be initiated either way, either by heating it to a high enough temperature or by light of an appropriate wavelength. You need a way to break that, Cl or Br. You need a way of breaking that weak halogen-halogen bond in either Cl2 or Br2. And either light of the appropriate wavelength, which I don't care if you memorize which wavelength, I don't think that's a good use of your time, or heating it up enough will do the job for us. And there's other ways of initiating these reactions too. We've got radical initiators that you can use as well. But be that as it may, in the end, you'll wind up replacing a hydrogen with a halogen atom, and the byproduct will be either HCl or HBr. So I'm just putting HX here, depending on whether you started with chlorine or bromine, respectively. So this type of reaction is what we call a substitution reaction. I'm assuming, again, in Gen Chem, you covered the types of reactions. There's basically 4 main classes of reactions. They're like what? Combination, there's elimination, or combination is also called addition, but elimination also called decomposition. You've got substitution, which this is a type of substitution reaction. And you've also got rearrangements, where something basically just turns into an isomer. Those are not terribly common, but they do happen. Certainly not as common as the other types. But in any substitution reaction, you find 2 groups switching places. That's what always goes on in a substitution reaction. And you guys must have done these in Gen Chem till they were coming out your ears, your nose, etc. You did precipitation reactions. Oh, you loved it. Lead 2 nitrate plus 2 sodium iodide yields lead 2 iodide plus 2 sodium nitrate. So the metals switch places and you get an insoluble precipitate. Acid-base reactions are substitution reactions. You basically have metals and hydrogen switching places. And this type of reaction is also a substitution reaction. You're basically swapping out a hydrogen for one of the halogen atoms on the halogen molecule. And so they swap places. That's not the mechanism of the reaction. The mechanism doesn't happen by the halogen molecule coming up next to the alkane. It's like that in one step. It's a little more complicated than that. The book goes into the mechanism of the reaction. And by the way, I don't expect you guys to learn the full mechanism of radical halogenation. And again, I hope this isn't coming across wrong. I don't mean it as an insult. I don't in the slightest mean it that like you can't handle it or something like that. It's just that I don't think it would do you any earthly good to learn that. I can't see any possible educational benefit that you guys can gain by going through all that. Or the amount of benefit you gain would be so small that I don't think it's worth your time. If it were something we were going to talk about for weeks and weeks later, that might be another thing. But I just don't see it as being that foundational. I will let you know, though, that you can see more information about that in the book. And also, I meant to mention, sometimes you will still get OWL questions on things that I said you don't need to know for the exam. So remember the general rule we gave the first day of class. If you want to know if you need to know something for an exam, in general, if it's in the book, you're responsible for it, unless it's something like just now that I specifically say, either in lecture or in the class notes, that you're not responsible for. So that's my blanket answer. That saves all of us those emails. If you want to know if you have to know something, if it's in the book, you have to know it, unless it's something I've specifically said somewhere that you're not responsible for, like I just did with the mechanism of radical halogenation. So I just don't think it's worth your time to take yourself through all that. It would take so much time and give you so little back in the way of benefit. I don't see it as being worth it. Good, so that's halogenation of alkanes. It's a substitution reaction where a chlorine or bromine molecule reacts with an alkane molecule and you swap out a hydrogen for the chlorine. So which hydrogen? Well, that all depends, and we're going to spend a little bit of time on that. And I want to go through some examples. Over here, I've basically given you a general, sort of the general framework or general description of the reaction. I haven't given you any particular molecules yet, and we'll certainly get to that. I do want to say, though, one very important thing about halogenation is that it uses an excess of alkane. And that's very important, because if you don't use an excess of alkane, if you use an excess of the halogen instead, then maybe this carbon or other carbons in the same molecule have other hydrogens on them, and you can get molecules in the end that have more than one halogen added in them. And that's usually not good. In other words, you'll get a mixture. We don't usually like getting mixtures. To the greatest extent possible, we want to get one compound out at the end. And we're going to see we still run into some problems even with a large excess of the alkane. But if we use an excess of the alkane, at least we ensure that all of the product has only one halogen atom in it. At least we don't get any multiple halogen products. So that at least solves that problem. As it turns out, the problems don't end there. At least we can sometimes run into other problems. Not always. Examples of particular halogenation reactions. Whoops. How about carbon having 4 bonds? That's usually a good thing, right? Let's say that we treated methane with chlorine, and we heated it or we added light of an appropriate wavelength. I think you'll find in the end, again, assuming a large excess of methane, that we will get chloromethane plus HCl. And in general, by the way, we're most interested in the organic product. That's something I think you'll notice as time goes on. In Gen Chem, you spend quite a bit of time talking about balancing equations. One thing I think you'll notice as we get further into it is organic chemists are kind of sloppy sometimes about balancing reactions. We don't usually care about the inorganic side products. Yes, you want to mention them if you want a balanced equation. But I think you'll find at times we just leave those out because we're so much more interested in the organic portion. We don't care about HCl, that's inorganic. So I think that's something you'll notice as time goes on. We sometimes get a little sloppy about balancing equations. But be that as it may, that's the only possible monohalogenation product, with one chlorine, I mean, because all 4 hydrogens in methane are the same. So it doesn't matter which of those 4 you replace with a chlorine, or for that matter, a bromine. There's only one possible product. And again, the reason we use a large excess of methane is because if we didn't, then the chloromethane could react with chlorine and give us some dichloromethane. And then the dichloromethane could react with chlorine and you could get some chloroform, CHCl3. And then even that could react with chlorine and you can get some carbon tetrachloride, CCl4. In other words, you get a big mess. And we want to avoid that if possible. We want to get just one clean product to the greatest extent we can. What if instead of methane we used cyclohexane? That's cyclohexane, 6-membered cyclic hydrocarbon, saturated. And let's say we treated it with bromine. Well, I think you'll be able to convince yourselves that all 12 hydrogens on cyclohexane are the same. So it doesn't matter which you replace with the bromine. There's only one monohalogenation product possible. And I'm going through all this to some degree because you'll find OWL questions on this topic. But I want to do some easier examples first where there's no issue. And of course, you would also get HBr, which we might or might not even mention, depending on how sloppy we want to be. It is there, and if you want a balanced equation, you need to mention it. But you'll find oftentimes we don't mention those inorganic side products because we care so much more about the major organic product. We don't care about the inorganic side products. Generally, there's something we want to remove from the organic product, and there's ways of doing that. Those of you who go on and take the lab portion of this course will learn a little bit about that. And that depends on what your major is. Some of you need it, some of you don't. So consult your advisor. But these were easy cases. Oh, sorry, we'll get into the difficult ones next. Yes. In other words, are you ever going to be replacing something other than hydrogen with a halogen? No. Nope, this is a reaction of alkanes. That now we will learn some reactions that say alcohols do, some reactions that carboxylic acids do, some reactions that ketones do, but they're different from this. They undergo different reactions. Basically, one thing I'm hoping you guys are getting across from this is there's really not a lot to say here. Alkanes don't do very much. They're quite inert. You can burn them, you can halogenate them. That's it. There is nothing else they can do. Otherwise, they really don't undergo very many reactions at all. In fact, I would say, if you can come up with a way to take some random hydrogen on an alkane and replace it selectively with anything else, you will become stupidly rich. And I will not begrudge you 1 cent of all that, because that's a big topic of research today. How to take what they call an unactivated hydrogen, just some hydrogen in some molecule somewhere, even in an alkane, and get it to react selectively with something else. But maybe that's neither here nor there. But hey, if that's you, great, more power to you. Good, other questions? Oh yes, I'm sorry. Yeah, how would you? Well, certainly you'd be right in the case of methane and chlorine. Both of those are gases. It'd be a pain to do that in the lab. You'd have 2 gas cylinders, and I would expect you'd want to keep everything very cold. I don't even know if you could get it cold enough to condense methane. Methane must have, I don't know off the top of my head, but I bet it's southward of minus 100 degrees Celsius. So, but you would use glassware, that's appropriate, and just have everything stoppered appropriately and make sure that you're not spewing methane and chlorine everywhere. That'd be bad. But usually we do reactions in glass vessels of some kind or another. The only time we don't is when you're using something like fluorine or HF that will react with glass, in which case you're probably better off doing a different reaction because then you have extra problems. But is that kind of what you meant? Yeah. Yep. Good. Now, in the case of cyclohexane and bromine, those at least are both liquids. So that makes it a little easier to do. But bromine is still exceedingly nasty. It's fuming red, ugh, horrible stuff. I've used it before. I'd rather use bromine than chlorine, but it's pretty nasty. Anyway, this is all fine. But what if instead we were doing the reaction with propane, which you could draw like that, or you could write CH3, CH2, CH3, same thing. What if we were reacting this with, let's say, chlorine? And again, all of these are going to use either heat or light. In general, you need one of those 2 in order to make the reaction go. Well, I think you'll find that there's actually 2 different possible monohalogenation products. Even, Cl2, sorry about that. Even if we have a very large excess of the propane, there's still 2 possible products. And I bet you're already seeing what they are. One of them would look like this, where we put the chlorine on that middle carbon, Those two hydrogens on that CH2 are equivalent to each other. Or we could take any one of those 6 hydrogens that are in the 2 methyl groups. They're all equivalent to one another. And so you would get that. You would get both products. You wouldn't be able to get just one product. It's not possible. So this is a limitation of the halogenation of alkanes. In cases like this, where there's multiple types of hydrogen in the starting material, we didn't have that in methane. All 4 of those hydrogens are the same. We didn't have that in cyclohexane. All 12 of those hydrogens are the same. So as long as you use a large excess of the alkane, you'll only get one product. But in even a relatively simple molecule like propane, there's more than one type of hydrogen. There's the 2 in the CH2, and there's the 6 that are in the 2 methyl groups. They're different from one another. And as a result, we get 2 possible monohalogenation products. And again, I'm only dwelling on this because I think you'll find some questions on this concept in the chapter 2 OWL assignment. And so how do you know that those 2 products are different from one another? Well, one way you can know that they're different is by naming the 2 compounds. And I think you'll find this is 2-chloropropane, and this one is 1-chloropropane. That's one surefire way to know whether 2 molecules are the same or if they're isomers, is by naming them. And if you get different names, they're not the same molecule. If you get the same name, then it's the same molecule. So this is kind of a feature, if you will, of halogenation of alkanes. Even if you use a large excess of the alkane, which is best practice, even if you do, it's very common that you'll get multiple possible products. This one is only 2. There could be 4, 6, 10 different products, depending on the structure of the starting material. But even in a simple case like propane, there's 2 possible products. And that cannot be prevented, by the way. There's no way to prevent that. So that means if you did this reaction in real life, if you took propane and you took chlorine and you mixed them, and you shone light on it of the appropriate wavelength, or you heated it at a certain temperature, probably wouldn't take too much heat, by the way. Chlorine's pretty reactive. But be that as it may, you would isolate, along with any leftover propane, you would isolate both 2-chloropropane and 1-chloropropane. And you can't prevent that. So if this is all making it sound like the situation is kind of depressing for alkanes, in that there's very few reactions they can do, and even the ones you can do are fraught with potential problems, then I would say you're following very well so far. There's just not a lot that alkanes do. So let me see if I have any other examples. I mean, I'd rather not take class time and do something with 17 different products, if you don't mind. But you can easily imagine if we took a much larger molecule than propane, there could be 3 or 4 or 6 different types of hydrogen. So you'd get 3 or 4 or 6 products. And so if you see any OWL questions that are asking about monochlorination or monobromination products, maybe how many there are, it's this concept that the question is covering. And so you'll figure out how many are possible. With propane, there would be 2 possible products. And by the way, 2, not 8. There are 8 hydrogens in propane, but there's only 2 possible products because there's 2 types of hydrogens. It doesn't matter which of the 2 in the CH2 you replace with a chlorine or a bromine, you'll get the same product. And it doesn't matter which of these 6 hydrogens you replace with your chlorine or bromine. They'll all give rise to the same product, either 1-chloropropane or 1-bromopropane. And again, getting into the product ratio and oh goodness. I mean, your book will often go into details about things like this. It'll say you get so many % of 1-chloropropane and so many % of 2. Of course, I don't care if you memorize that. I would never ask you to memorize like particular % yields or anything like that. Please, that's not anywhere close to being a good use of your time. But certainly if there are helpful trends, as an example of something like this, I said electronegativity. I said, certainly you don't need to memorize all the Pauling electronegativity values. But I would kind of like you to know the trends for electronegativity, that it increases from left to right and it increases up the periodic table. That's important, I think. But I would never ask, what is the electronegativity of oxygen? No way. I don't want you just memorizing loads of numbers. I'll use the same phrase, not a good use of your time. Good, so I think that's about all there is for that. I do want to talk a little bit about intermolecular forces. Any other questions on halogenation of alkanes? Yes. Yeah, they're different compounds. And if you tested the product mixture, you'd see that both were there. Well, that's just it. Excellent question. And the answer is no, there's not just one propane. Remember, when you do a reaction, there isn't just one molecule of the propane. You've got like 6.02 times 10 to the 20th molecules, some of which will turn into 1-chloropropane and some of which will turn into 2-chloropropane. And others, by the way, which wouldn't react at all because we have an excess of the alkane. So, but that's actually a very important point that you're bringing up. It's important to remember when we're talking about a reaction that there isn't just one molecule of that starting material floating around in space. There's billions, trillions, quadrillions. Is that kind of what you meant? Yeah, yeah. It's an excellent point, and it's something important to bear in mind as we go on. There's not just one molecule floating around in kind of this theoretical space. There's 10 to the 10th, 10 to the 15th, 10 to the 20th molecules. Good. Other questions then? Oh, yes. That was resonance, and that's just it. Remember, with resonance, it really isn't two things. That's the hard thing about resonance. It really isn't flipping back and forth between two things. So this is not resonance. That's exactly right, exactly right. Resonance is a phenomenon that speaks of a molecule that is one real structure, but that structure is at all times a hybrid of two or more structures. And exactly, this is not that. This is not resonance. Another excellent point. Yes. How do I know if the hydrogens are different? Well, answering the question if the hydrogens are different or the same is the same as asking whether the products are different or the same. So what you do is you try one, you replace one with your halogen, and then you move on to the next one and you replace that with a halogen, and you see, are the two the same or not? Which again is a non-trivial skill that takes practice. But yes, I don't expect you to just look at the thing and go, oh, there's 5 products. No, you have to try. And you'll see how many different possibilities you can come up with. And then you'll look at some of your structures and go, oh, these two are the same because they have the same name. That's kind of how you'll do it. At least that's what I would suggest. Good questions, though. Yes. Oh, well, yeah, you can find yourself going down the chain and getting a different one each time. Yes. Yeah, well, change H to halogen and see if you get a different structure. And if you're worried whether you've got one or not, you can just name the compound. And if you get a different name, it's a different compound. But I just wanted to make sure you said saturated. I don't think you're talking about unsaturated compounds like alkenes, because those are a different critter. Yeah, but you're just saying, what if it had several different chains on it? I think. Yeah, it's okay. I don't mean to come down on you, but yeah, then you just try all of them and see if you get a different compound. Yes. Hydride shifts. Whoa. I don't think we'll see anything like that until we talk about the reactivity of alkenes. And even then, I'm not quite sure we will. We'll find out when we get there. It's been a while since I've taught this class, but certainly not here. That's not good. I'm not aware of anything like that happening with these radical reactions. So I guess my simple answer to your question is not until later. We'll get to things like that. Good. No, it's great. I love the curiosity. Good. So much for halogenation. let's maybe do a sort of quick thumbnail review of intermolecular forces. I only have 6 minutes anyways. And if I get to start talking about conformations of ethane, great. If not, it's not the end of the world. We can take care of that next time. Good. So in terms of intermolecular forces, remember that these are going to be properties of molecules that have to do with, as the name implies, forces between multiple molecules or among multiple molecules of the same compound. And these are the presence or absence of these will affect the properties of those compounds. And I think you've talked about hydrogen bonding. You know, hydrogen bonding occurs whenever you, especially what you want to look for with hydrogen bonding is OH or NH bonds. Those are going to be what you want to look for. I guess technically HF also undergoes hydrogen bonding. But it seems to be those three atoms, and they're all next to each other in the periodic table: oxygen, nitrogen, fluorine. Nitrogen, oxygen, fluorine, rather. There seems to be something about an atom being both small and quite electronegative that seems to cause hydrogen bonding to occur. And remember, hydrogen bonds exist between the hydrogen attached to a nitrogen or oxygen and an oxygen or nitrogen in another molecule. So there are forces between molecules. And when hydrogen bonding exists, when any of these intermolecular forces exist, it means that you have to put in a little more energy in the form of heat, let's say, to melt the solid or to boil the liquid. That's one of the main things that I mean, we could talk about viscosity. That's all fine. But my point being that there's multiple properties of the substance in bulk that come about from these intermolecular forces. You would have talked about hydrogen bonding. You would have talked about dipole-dipole interactions in polar compounds. We talked a little bit about polar bonds and polar compounds in chapter 1. I didn't spend a lot of time on it because, again, it's reviewed from Gen Chem. The only intermolecular force that you're going to find in alkanes is going to be dispersion forces, or your professor might have called them London dispersion forces, or your professor might have called them van der Waals forces. There you go again. Yet another example. They all mean exactly the same thing, but we have 3 terms. Chemists are just never happy unless there's at least 2 different things to call any one phenomenon. I don't know why that is. But the dispersion forces, or van der Waals, not van der Waals forces, although it has 2 A's. I had nothing to do with it. Or van der Waals forces, whatever you want to call them. Those are going to be the only intermolecular force that's viable when you're considering alkanes. So alkanes will not undergo hydrogen bonding because there's no OH or NH bonds. So you do need to have OH or NH bonds for there to be hydrogen bonding, which, by the way, it's not enough just to have an oxygen or nitrogen in the molecule. You have to have at least one OH or NH bond in order for there to be hydrogen bonding. And alkanes don't have that. So that's why alkanes don't dissolve in water. If you added vegetable oil, which is mostly hydrocarbon, to water, it would not mix. You'd get a layer of the vegetable oil on top. We know that from daily experience. Gasoline would do the same thing. I don't know how often we're pouring gasoline into water, but if you did, you would find the same thing. You would get a layer of the hydrocarbon on top of the water. So that all gets back to this idea of like dissolves like. Let's see. I mean, I think it's important to be able to tell something about what intermolecular forces you'll get. In terms of, for instance, just to end with one particular example of an intermolecular force, hydrogen bonding. You know, you could pick a big molecule like glucose. I'm only bringing it up because A, it's in my notes, and B, I doubt you've seen it before. But this is the structure of glucose. And no, of course, I don't care if you memorize this. That's not the point. I'm assuming you've heard of glucose. It's also called grape sugar or even sometimes blood sugar because it's the main way that carbohydrates are carried in the bloodstream. CH2OH. Well, it's no big surprise that glucose is water soluble. Look at all of those OH groups. This thing is undergoing hydrogen bonding like crazy. So it will hydrogen bond also with molecules of water and therefore dissolve in water. Whereas again, something like vegetable oil would not. And actually, I'll tell you what, I went a minute over the other day, so I'll end 30 seconds or a minute early today. That's a good place to stop. And we'll pick up with conformations of alkanes and cycloalkanes next time. Have a good day. I'm listening.